Rahim. Welcome to Keep Talk. Those of you who are joining today from different parts of the world, including USA, Canada, London, England, Australia, and some other parts of the country. Welcome, all of you. We started Keep Talk for one reason, is to learn from each other, and whatever we learn, try to also share with each other. It is impossible for anybody to read all the books in the world, so we started this as a complement and learn from each other. So you'll see it says Keep Talk. So our motto is basically keep on learning and keep on sharing. This session is being recorded, and it will be shared on the social media. So any of you do not like their faces to be shown, kindly, you can put the stop video, and let us talk about some housekeeping before we start our session also. We request that you put your mute button so that to minimize all the background noise. When the chat session comes in or you speak to the host, then you can unmute yourself and talk on one-on-one. Second, if you have any questions, we have a chat session also. You can type it there, and we'll try to pick it up after the guest speaker finish his talk. We'll go to Q&A, and from there, you can ask him direct question or type it on the chat session. We'll try to pick it up from there. You can also raise your hand, I believe. If you see the button, you can raise your hand when there is a Q&A session. What we'll do once our Q&A session is done, we are going to also unmute everyone, and you get to talk to our guest speaker for tonight on one-on-one. So everybody would be unmuted, so you can, just like a hangout, you can hang out with him, ask more questions, get to know him, or you can talk to each other. So that's it. I welcome all of you again for joining us on this Sunday afternoon here. Today our topic, as you know, is quantum computing and networking. I'm going to share my slide right here. I think you should be able to. Okay, and we have heard many things about quantum computing. And if you see, the computers are getting smaller, the chips are getting smaller and smaller, and it's computing faster and faster ever. Yet, you will know that there are so many computing and complex issues that we face today that cannot be solved by today's technology. And that's where we see quantum computing comes into play. So many people are super excited, including companies like Google. They already declare supremacy, but that is not kind of true. I think maybe it's a fake news. They achieved something, but not all the way. IBM is another one that achieves so many things on the quantum side, but no one has any supremacy in quantum computing yet. Quantum computing for today's topic is basically it's quantum and computing. Now, when you think about computing-wise, of course, the computer science type or mathematics or finance. Quantum side, mostly, at least for me as a layman, I can think of, is more like an electron running around. And you're right that that's actually going to be how to use all these quantum mechanics to use them in also solving other problems, including powerful calculations and things like that. Are you able to see my screen? I just want to make sure.
Yes.
Okay, great. So from today's session, we are going to learn about quantum computing, networking, the progress has been made so far, and what's ahead and future of both computing and future networking, which mathematician, physicists, chemists, they are super excited just to see what is going to happen and how we can take advantage of this coming technology that we are going to see in near future. It could be within 2 to 10 years, I believe. Our guest speaker will tell you more about this. Tonight, our guest speaker is Dr. Moshiur Rahman. He is a principal scientist in AT&T Labs. Dr. Rahman joined AT&T in 1987. He currently leads AT&T operation, machine learning and automation team in advanced wireless and communication division. Dr. Rahman also worked different research areas, including switching, signaling, wireless communication, virtualization, etc. His current areas include advanced analytics, future wireless communication, and quantum machine learning. I am very excited to tell you that he is one of the lead inventors in AT&T research, has 74 patents and 310 patent disclosure. He received his MS in electrical and computer engineering from Michigan and a PhD from Stevens Institute. He is also an adjunct professor at Stevens Institute of Technology and NJIT, teaching graduate courses in computer science, in quantum computing and TCP/IP networking client-server programming. Besides his all this accomplishment, he is, when I spoke to him last time, I think he jogs every day. 2 times I called him and he was jogging, so I can tell, even though he did not mention this, he's also a good runner, I believe. He also enjoys reading, traveling, and he also enjoys watching cricket. And the other hobby he has is fishing. He is actively involved in many charity programs, nationally and internationally. He helped establish a women's college in a remote area of Bangladesh in 2010, and local people named the college after him, Dr. Moshiur Rahman Women College. So we are very proud of you, Dr. Moshiur Rahman, on that. I would like to welcome you now. Welcome, Dr. Moshiur Rahman. Please start your session. We are humbly requesting you to start your session now. I'll stop sharing and so that you can start your screen.
Thanks, Soel. Can you see my screen?
Yes.
Yes, very good. So, Soel, thank you very much for this session arranging. And at the start, I'd like to remember those who have left us and those who are suffering in this very difficult time. We know in our cadet college community, we have lost quite a few, and this is very difficult time for us, and we'd like to remember them. So I guess that this talk is on quantum computing and future networking. Basically, we call it quantum internet. Now, the quantum mechanics is the underlying foundation of quantum computing. Now, the quantum mechanics is weird, it's complex. And, according to quantum mechanics, a Coke bottle should be able to exist in a superposition of 2 locations, both here and there. It's a weird concept, but it is true. So I have been thinking how I should package this talk. And I really wanted to make this talk less technical, but when it comes to quantum computing, quantum mechanics, right, it is kind of challenging. But anyway, I'll try to make this talk a storytelling, entertaining, and hopefully it will be easy to understand. So now, as Soel said, quantum computing, and this is a new way of performing computation. right? And it's a quantum computer is a machine that you can see here, right? That performs calculations based on the laws of quantum mechanics, which is the behavior of particles of subatomic level, right? So you see, this is a picture of a computer, quantum computer, and this kind of computer sitting only in some buildings, some locations, primarily those research like IBM, Google, Microsoft, Rigetti, right? Because these are being, used for research purpose mainly. But one thing you see, the color is gold, right? And it is made of gold. Typical quantum computer is having about 2,000 components, and all of them are made of gold. And in terms of cost, the very first computer was sold that was made by DOF, a Canadian company. It was sold to NASA, and that was in 2016. And the price was 16 million, right? So it's a kind of, you can see the shape of this is kind of hanging chandelier kind of thing, right? Now, question, why it is hanging off the ceiling? Anybody can guess? Because the unit of quantum information, what you call that, I'll go over that, qubit, quantum bit, is very sensitive to outside environment. Okay, so these qubits must be shielded from all external noise. Okay, and this is, this should be free from all this radiation, and the temperature, the current operating temperature of quantum computer is minus 273 Celsius, which is 15 millikelvin, equivalent to minus 460 Fahrenheit. You see, so it's kind of temperature that is colder than outer space, and that's where the quantum processor sits. All right, so it's you have to have some special environment to have this computer. And as I said, it is not commercially available, only in research kind of environment. Okay, so now with the breakthrough in science, there is the potential for new technology. For over the decades, the researchers have done inspiring work in quantum mechanics, transforming it from a theory for understanding nature into a fundamentally new way to engineer computing technology. Now, this is basically, quantum computing is a growing field at the intersection of physics and computer science. So this field, quantum computing, is beautifully, interdisciplinary and impactful in two major ways. Number one, as I said, it reorients the relationship between physics and computer science. Secondly, it can simulate nature at its most fundamental level, allowing us to solve many deep problems in quantum chemistry, for example, artificial intelligence, materials discovery, and so on. So, let me see how I go to the next slide. Okay, so you can see, so my talk will center around three areas, including brief history. And the three areas would be the quantum computing, quantum networking, and some progress and prospects made in this area. So, as I said, I have been thinking how to package this talk. I don't expect you to understand everything I'm going to say, but three things I would expect to remember at the end of the talk. The three things are the quantum bit, which is qubit. You can see that QSE, qubit, and the two important ingredients of or property of qubit is superposition and entanglement. In the last talk, Professor Moshiur Rahman, I think, went over this briefly, describing what is superposition entanglement. So I would expect you to remember these three terms. Again, the qubit, quantum bit, superposition, entanglement. Okay, So this superposition, this is the game changer. This is the heart of this quantum computing. All right. So the superposition is one of the properties that allows quantum computing to supersede classical computing. All right. So a qubit can exist. I'll be repeating this kind of expression many times in my talk. A qubit, a quantum bit, can exist in multiple states simultaneously. It's basically the essence of the principle of superposition. That happens because of the wave nature of subatomic particles in quantum mechanics. And it is hard to grasp something can be two things at the same time, right? And because it's totally alien to our everyday experience, like a car is not simultaneously a bicycle or a bus. But that kind of concept is true in quantum mechanics, right? So in quantum theory, however, that's just the kind of crazy thing that can happen. And most striking example that Dr. Rahman, I guess, shared with us, right? So example of this baffling riddle known as Schrodinger's cat. Briefly, in the weird world of quantum theory, we can imagine a situation where something like a cat could be alive or dead at the same time. So you see, this word, this concept is in the core of this quantum computing. You can see in this diagram, you see the electrons can exist in multiple states at once. That means this superposition can give us the unparalleled parallelism in quantum computing. All right, the true parallelism comes from the superposition. Okay, so the qubit, I just said, is basically is a quantum concept of a bit. It is not an element or device. It is a logical concept that can be implemented on a wide range of different systems with quantum behavior, like electron, photon, atom, and so on, right? So as I said, the superposition is the game changer, and this is the heart of this quantum computing. And the quantum computer uses the path of this particle, electron, right? Path of electron, and path of electron that encodes the information. That's the key. So let me go to the next slide. Now, as I said, I want to make it a little bit entertaining, right? And storytelling. So the quantum physics is one of the most successful theories in modern science that explains how the world works at the most fundamental level. These are the brains behind quantum physics. So now I have a quiz, right? I want to ask you 3 quizzes. Number 1, tell me here one of the scientists, right? Born in Poland, and that scientist got more than 1 Nobel Prize. You see the circle? These are all the Nobel Prize winners. But my first question is that, find out here from this picture, a scientist was born in Poland and got more than 1 Nobel Prize. That is number 1. Question number 2 is, name 2 scientists in the front row, born in German, happened to work in the University of Berlin. Number 3, you can point out who is here, who developed the theory of uncertainty. So these 3 quizzes I have, I give you maybe 50 seconds, and give me the answer if anyone knows.
Yeah, the first one could be.
Question 1 is Madame Curie.
Yeah, Madame Curie.
Yes, good.
And second one is Einstein.
Einstein. And third one would.
No, I said 2. I said two scientists happened to be born in German and also happened to work in University of Berlin.
Einstein and Oppenheimer.
Yep.
And the third one is Schrodinger.
Schrodinger.
Who developed the theory of uncertainty?
Schrodinger?
Heisenberg.
Heisenberg,
Okay.
right.
Heisenberg.
Heisenberg.
Good. So you can see this, right? I mean, you see this, all the circles, those got Nobel Prize, right? And you see the Planck is one of them, and you said Einstein, and the Curie, right? She was born in Poland, and then she immigrated to France, and that's where she lived. And Heisenberg, you can see there, right, on the top standing. So these are the brains, behind this quantum mechanics, quantum computing. Good. So Kaunbhai will get a prize, right? And who said it? Second one.
Vibhas.
Good, Vibhas. Very good. All right. So this is basically, we are saying that the quantum computing is a blended version of quantum mechanics and computer science, right? And the quantum computing has become one of the leading applications in the quantum physics. And as I mentioned, the quantum computing is based on the principles of quantum mechanics, right? Which provides a description of the behavior of very small atomic and subatomic particles. Now, the quantum computers utilize the certain properties of subatomic particles in conjunction with the theories of computer science to process and store information. This merging of quantum mechanics and quantum science has been extensively explored during the last 3.5 decades and has led to development of technologies for a class of computational problems like factorizing large number and searching for unsorted collectors, right, or data. So I'll go over this in detail, but my message here is that the quantum computing is a blended version of quantum physics and computer science. So these advances in information processing capability can be attributed to the fact that data bits in quantum computers can simultaneously exist in more than one state at a time and can be manipulated simultaneously. So you can see the right-hand side, that's another picture of a quantum computer. And I didn't mention, the temperature is, from top to bottom. For example, in this computer, it's IBM computer, and the temperature, decreases. The top, the temperature is 300 Kelvin. You go to the middle layer, it's about 4 Kelvin, and you go to this end, that's the qubit chamber, and that temperature is about minus 460 Fahrenheit, which is 15 millikelvin. Okay. So the quantum computer is, as I said, it's a machine that performs calculations based on the laws of quantum mechanics. Basically, that is the behavior of particles at the subatomic level. Okay, now this is, if you wanted to simulate nature, you should build quantum computer. I'm going to explain what that means, how it is created and problems that it will solve. But before that, just, I got to tell you what it is, a fundamental idea, right? And the fundamental idea is just like we have bits in classical world that can be a 0 or 1, right? And I know there may be some students here, I'm not sure, but I just want to give a few more words on this concept of 0 and 1, right? So information represented in our classical computer as 0 and 1. Now, in fact, every classical computer translates these bits into human readable information on your laptop or phone. And for example, the Word document you read or video you are watching is encoded in the computer binary language in terms of these ones and zeros. Now the computer hardware understands the 1 bit as an electrical current going through a wire. Wire is basically a transistor, right? While the 0 bit is the absence of an electrical current in a wire. So the electrical signals can be thought as of 1, the bit 1, or off the bit 0. So your computer then decodes the classical 1 and 0 bits into words or videos and so on. Okay, so this kind of high level of idea about the information about bits. Now, in quantum computer, right, you see the right-hand side, that's a qubit. Qubit can be, see, 0 and 1, the North Pole and South Pole. But we are interested not in North and South, we're interested in between, right? Between 0 and 1. That's where the superposition happens. Basically, this you see the right-hand side is kind of pictorial view of a qubit. Okay, so in quantum computer, you have qubits, which stands for quantum bit. Now, the difference is that there can be 0, as I said, 0 or 1, or both at the same time. And that exploits the principle of quantum physics called superposition. It sounds weird and crazy, but it is true. So I have more on qubit later on, just to get our feet wet in terms of qubit and bits. So here is I just want to let me shed more light on the concept of superposition. I think Professor Moshiur Rahman, he explained this Schrodinger's cat, but let me go through a little bit slowly here, right? Using Schrodinger's cat, famous thought experiment. So here the Schrodinger's cat is placed in a closed box, right? With a single atom that has probability of emitting decay radiation at any time. Since radioactive nuclear decay is a spontaneous process, it is impossible to predict for a certain when the nucleus decays. Therefore, you do not know, therefore you don't know whether cat is alive or dead unless you open and look in the box, right? And it can be said that the cat is in both alive and dead with some probability. So that is, the cat is in a superposition state until you open the box and measure the state. So upon measurement, the cat is obviously either alive or dead, and the superposition has collapsed to a definite non-state. For example, it could be 0 and 1, which is dead or alive. So quantum systems can exist in a superposition state, and measuring the system will collapse the superposition state into one definite classical state, which is 0 and 1. So now this might be hard to understand from a classical point of view, as we usually do not see the quantum superposition microscopic level. So, let me just share a story. Like Einstein was really bothered by this feature of quantum systems. And his friend Abraham Page recorded, that he said that I recall that during one, Einstein suddenly stopped and turned to me and asked whether I really believe the moon exists only when I look at it. You see? So the superposition is a kind of situation or phenomenon that you don't see it until you open it. Okay? So the Schrodinger's cat, the famous thought experiment, was designed to show if quantum mechanics is taken literally and its ultimate implications, even microscopic systems like cats would be in such superposition of states, like cat being both dead or alive, which is a kind of apparently absurd conclusion, but that is true in quantum mechanics. All right, and the right-hand side, I didn't want to explain it. Basically, I explained in my class, for example, this is the expression we use, you might know this wave function, right? Wave function is basically the linear combination of two states, 0 and 1. In this case, the 0 is called the cat could be dead, and 1 could be the cat is alive. So this the wave function we call the qubit, right? Is in a state of 0 and 1 simultaneously. That is cat alive or dead simultaneously. So that's the notion we use in quantum computing to perform this parallel computation. You can ask me a question, at the end of this. So let me move on. So now you see, as I said, I'm trying to be away from mathematical expression, but it's difficult. So now to give you this unease that you should feel when you talk about quantum information and quantum computing. So I'm going to give you a very simple example, right? A thought experiment that happens to be true. So let's imagine that we are going to solve this problem. The problem involves you have 4 cards. 3 are identical, 1 is different, and different is queen. So we shuffle the cards and put them face down, and problem we are going to solve together here is find the queen. Okay, so now we are going to be assisted by 2 computers, right? 2 computers to solve this problem. One is classical, one quantum computer. So what we do is we turn them down and we load them into memory. So we use 4 memory slots. The cards identical, we put zeros, and the one that has a queen, we put a 1. We load them into 2 computers, as I said. Now we have to write a program to find this queen, find the 1. How it would be done classically, right? So you would go classically, right? In classical computer, right? You would go and pick a random number, and you don't know where it is. You go under the memory slot, see if it is a 1. If not, you go to the next slot, and so on and so on. See, on average, it would take you equivalent of 2.5 turns to find 1. So the summary is that you are having, more than 3 operations to find 1. Now, magically, it turns out that with the 2 qubit, why 2 qubit? Because we have 4 states, right? So I need 2 qubit to represent 4, right? So now it turns out that with a 2 qubit quantum computer, for this problem, you can always solve in a one shot, single shot. You need 1 operation to find this queen. Whereas classical, I might need more than 4 operations. So now you can see the power of quantum computing, right? I'm just, giving this example, but mathematically we can show that too. But as I said, I'll not be using mathematics because I'm not going to test you. I do that in my class. So now, so that this uneasy feeling that you have when you say that the cat can be alive and dead same time, now you should be an explanation that quantum computer is not just about, building faster computer. It is building something. It is building something is fundamentally different than a classical computer. Now, a way to think about is the abstraction of it is that a quantum computer is always going to have a classical computer, because I'll see, right now, you need to have classical computer to prepare your programming, and then you send this information to quantum computer, and you get the result back, and then you use a classical computer to get the result. I will have some slides to illustrate that. So you have a classical set of bits, right? The problem you are trying to explore, and what that quantum computer is going to allow you to do is explore this exponential number of states, right? Like this 2 to the power n. N could be anything. In this case, my qubit, this 2, 4 states, right? Where n is the number of qubits that you have. So now you have relatively small quantum computers with few qubits. But think of the number of, by the time you have 50 qubits, you know, we're talking about this Google, right? Google has done, they call it quantum supremacy. They have used 53 qubit, 2 to the 53. So you have this 2 to the 53 or 50 states. That's a phenomenally large number, right? By end up, you explore the states, you go back to classical computer to get the output. So that's kind of, you know, explaining how this quantum computer is going to play a role in the future in terms of computation. All right. So the next one is at the right-hand side, I mentioned this classical and quantum computer. Basically what is happening here is the following, right? So here is, I have this quantum computer, you know, sitting in the chamber. You can see that the temperature of this qubit where it's sitting is a 15 millikelvin, which is minus 460 Fahrenheit or minus 273 Celsius. So basically, you know, right now what is happening, you have this problem, you're writing this code, you know, in classical computer, you're compiling it and sending to this classical computer, I mean the quantum computer sitting somewhere in some cloud, right? So that's why I said that you need to have classical computer in order to carry out any experiment that we like to have with quantum computer. Let's move on. I have 2 more examples. So here is another example to illustrate the power of quantum computing, right? So there are a large number of problems in the world that have these characteristics that they blow up exponentially. And a dirty secret in world of computing is that we obviously talk a lot about, you know, all the things that can solve and can solve a lot of things, but there is a lot of things that computers cannot solve, and very, you know, interestingly, that they cannot solve now or ever. So here is, you know, I'm going to illustrate this. You know, here is that, you know, and reason is because that they have this exponential built into them. So take an example here. Take an example. And this is fairly a simple equation, factoring, right? So here is, you can see m equal to p and q. So I have a number m, right? And that is made out of multiplication of 2 large prime numbers. And I only give you m and ask you find me the p and q, right? It turns out that it is phenomenally difficult to solve. Think this, you know, I mean, there is no other way but to divide it, you know, start off, you know, sort sequentially prime to numbers. So in fact, it is so difficult, we use it, you know, as the basis for all encryption today, right? But if you have very large universal quantum fault-tolerant quantum computers, which is many years, I mean, many years away, you could solve that problem in seconds. You can see this, right? It's taking, you know, billion years, but it can be solved in this case, in 100 seconds, for example, right? So you know, you could solve that problem in seconds. What would take billion of years in classical computer? That tells you something about the power of what is going to be possible, right? So that's an example, and I'd like to give one more example. You know, it's kind of mathematics in the power of quantum computing. Here is that the main advantage that quantum, as I said, computer have over classical computers is parallelism that comes from superposition, right? Because quantum bit can be in a superposition of a states, a quantum computer can perform an operation on all of the states simultaneously. So here is the, let's say in the right-hand side, right? The right-hand side, let's say we want to know the result of applying some function f of x to some number x, right? So look at this, the right-hand side, the classical computer. So the classical computation, two classical computations are needed to find the result x equal to 0 and x 1. Whereas a quantum computer can, solve this, both answers in parallel. Why? You can see this, the A, we call ket 0 plus B ket 1. You feed this information to quantum computer, you can get result with single operation because of this superposition of 0 and 1 simultaneously, right? So meaning a quantum computer with one qubit can operate on two classical process of information at once, right? Now the right-hand side, another example, right? You say given in this case, if you wanted to compute f x equal to 2, like you need 2 bits, right? And x is 3, right? So we need to add second qubit to the first one that we have done. The 2-qubit quantum computer evaluate all 4 possibilities at once. So look at this on the right-hand side. I have, if I go with classical computer, and it will, it will take 4 operations to perform this. If I go to quantum, 2-bit quantum, it takes 1 operation. How all this possible? Well, answer is superposition. The phenomenon of superposition allows quantum computers to perform operations on 2 bits of information at once with a single qubit, right? So that's kind of thing that, we can get out of quantum computing. So it is, the quantum computers solve the problem that would take infinity long in a classical computer. Things like, modeling your brain, modeling the weather, modeling any molecules, the chemistry. So that's kind of thing that quantum computer will bring for us. Now let's see some why quantum computing, as Sohail said that you see you have this this iPhone, right? Can you tell me how many transistors this iPhone has, like your iPhone 11 whatever? Any guess? How many billion transistors in your iPhone today? Anybody can guess? Give some number.
5 million?
2 billion.
No, it's 8.5 billion transistors in your iPhone 11.
Yeah.
8.5 billion transistors.
Question
So
is,
you see,
what is the size of each transistor then?
it's less than, I believe.
Avoid doubt.
Yeah. So computer technology is making devices smaller and smaller and reaching a point where classical physics is no longer a suitable model for the laws of physics, right? So that's kind of motivation. The transistor cannot be made smaller. The laws of quantum mechanics start to take over. That is the starting point. Okay. So here is, you say this, another thing that I'd like to mention, the quantum technology is making devices smaller and smaller, right? And we need to transit to, another domain, which is the quantum mechanics, right? Quantum computing. Now, one thing I want to mention here that, look at this, and I put this circle, right? So basically, anyone can guess, when you have your iPhone, right, and you are using, it becomes hot. What's the reason? Anyone can tell me? Any computer scientist? It's because of loss of information, and that creates heat, right? The loss of information that creates heat, resulting heat.
You're telling about entropy? Yes.
So yeah. So I'd like to just make this point so that you can see another motivation of so So the loss of energy, in classical computers that use classical gates, we call quantum gates, classical gates. And in classical gates, right, gate is used to manipulate in our classical computer, gate is used to manipulate the bit, right? So gate is realized through transistor. So in classical computer, it is non-reversible. In classical gates, its energy dissipation results due to information loss. And there's a physicist, IBM, showed that the loss of each bit of information leads to at least, this is the kT log 2 amount of energy released in the form of heat. So although this is a trivial amount of heat, it becomes significant in any computing system when do multiple big operation. So such a system carries out many millions operations per second. As a result, it becomes noticeably hard in a short amount of time. The loss of information and resulting heat can be avoided by replacing classical gates with reversible, and reversible gates come from quantum computing. So that's another motivation, right? And the gain we can get out of quantum computing. So, all right, I think we're running. So this is another, classical computers that we use this encryption. RSA stands for, this is the, encryption algorithm used starting 1977. All right, this is one of the first publicly encrypted systems, and is widely used for secure data transmission here, right? So we cannot use classical computer to factor the prime number, right? And simulation, now the quantum simulation inefficient with classical computers. And this scientist, the Feynman, I mean, he was the one, thought about this quantum computing very first time. But he was the one, basically a Russian scientist, Yuri Manin, he was the one and first proposed the idea of quantum computer. And then another scientist, he described this mechanical models of computers. And then 1991, 81, 82, the Feynman, he was professor in MIT. And so he presented a logical computer model first time and demonstrated a quantum system cannot be simulated with a classical computer. So that's where all the research started. Okay, so here is kind of the history of quantum computing, all right? And you can see this starting 1935. That's where the third paper that Einstein, I guess, he published. There's three scientists, EPR, Einstein, Podolsky, and Rothstein. So that's the paper, outlined the concept of entanglement, and that is the very, very important phenomenon that we use today. We'll be using in quantum computing. All right, it is useful and powerful. It means that, like observing one qubit can reveal the state of other qubit. So that's the starting point. A lot of research have gone since then, and Professor Shapiro knows more than any of us here. But you can see how we traveled from 1935 to up to this point, 2019, right? All these things. That 1982, that's the first quantum computer by Professor Feynman. And then these are the yellow is saying that the existing number of qubit in computer. And 2019 in October, right? That's where the Google declared their quantum supremacy here, right? And let me just, this is the computer that used by Google in their research lab. It's a 53 qubit Google Sycamore computer sitting in LA somewhere. So here is that, you can see the right-hand side. This is the quantum computer that Google has used. Basically, what they have done here, right? They have used 53 qubits to do this experiment, all right? So it was in the last year, October 23rd, 2009, Google claimed to achieve this quantum supremacy with just 53 qubits, performing a calculation in 200 seconds that the company that estimated would take the world's most powerful supercomputer 10,000 years. Think about it. this operation was done in 200 seconds, which is 2 hours 30 minutes, right? I mean, but the classical computer would have taken 10,000 years. Well, as Sohail mentioned, IBM kind of argued that the classical computer might do this kind of operation in 2.5 days. So IBM came in and disputed that claim, but nonetheless, it's a big achievement in this quantum computing paradigm. All right, so let me go faster. Basically, as I mentioned, all these quantum computers use atoms, the quantum particles, atom, photon, all these kind of things. And it depends on principle of quantum theory, which is superposition. And the 3 things I mentioned that you need to remember, right, from this talk: the qubit, the fundamental unit of quantum computing, superposition, that qubit can be in this state of superposition, and entanglement. Okay, so here is again mentioning same that works with quantum parallelism that comes from superposition, entanglement, and keeps the coherence. That means to maintain the superposition in this environment is difficult. Okay, so here is a little bit, and I want to go through this slide. So basically, I mean, I'm trying to summarize the difference between classical versus quantum computer. Okay, so conventional or classical computers are built from billions of transistors, as I said, right? And that are turned on and off to represent what? A value of either 0 or 1. In turn, this allows classical computers to store and process the data using binary digits or bits. In contrast, in the right-hand side, right, quantum computers process information using the quantum bits, which is qubit, can be represented by superposition, as we said, electronic circuit. Because of the strange property of quantum mechanics, qubit can exist, as I said many times, in more than one state or superposition at exactly the same time. This allows the qubit to assume a value of 1 or 0 or both simultaneously. So both of these numbers simultaneously. In turn, this enables a quantum computer to process far higher number of data possibilities. So that's the difference, So this true parallelism comes from this superposition, which is 0 and 1 can exist simultaneously. All right, so here is the same thing, the right-hand side, the data unit is bit, and quantum computer, the data is qubit. And you can see this is the wave function, which is basically a linear combination of 0 and 1. Okay, I don't want to describe this thing, it takes some mathematics, but nonetheless. So here is in the qubit is basically unit of quantum information. And these are the ways that you can build qubit. I'll go through in detail a couple of slides later on. All right, so here again, I said it, right? The qubit is a concept, right? It's a quantum concept. It is not an element, not device. It's a logical concept that can be implemented in a wide range of different systems of quantum behavior, like electron. Electron, we can say electron is a qubit because electron can exist simultaneously in 2 states at the same time, right? It's a 2-state system. Photon. So qubit is not a device but it is a particle, right? That can take 2 positions at the same time. And the bottom, you see this again, the wave function we use to describe qubit. It is basically the combination of the basis states 0 and 1. Okay, so I guess, and here is as I mentioned before that this describes the function, this wave function describes the quantum state of a physical system. But unlike the classical physics, where a complete specification of a state determines all of these properties, right? For example, the particles, portion, and velocity. The quantum state in general only gives possibilities of, in probabilistic view, predictions. Now, the next slide is a little bit, is just, again, the pictorial view of the qubit. And we use this, explaining, we call Bloch sphere. He's a scientist. So in this, Bloch sphere representation, a qubit can not only be in either north or south pole, right, of the sphere, but also in the states that are between the 0 and 1, 2 states. In other words, qubit can exist multiple states simultaneously. This is basically the essence of the principles of superposition that happens because of the wave nature of subatomic particles. Okay. So another slide, again, this is the right-hand side. This is a quantum state superposition, right? And can be written, in a linear combination of 0 and 1, where the psi is a qubit. 0 and 1 are the, this is the computational basis. And the alpha and beta are the complex numbers. This is the probability amplitude, okay? So this is a mathematical model of qubit, right? This basically the state of qubit that can be in two positions, two states simultaneously, 0 and 1, with some probability. All right, now this is the, this qubit can be realized with this kind of, physical realization, right? You can use photon. You can use photon in a polarization. You can use photon circular polarization. You can use the electron spin. Okay, you can use the quantum dot. So these are kind of ways that you can build, you can realize qubit. Basically, these are quantum particles, right? And here is, I want to summarize classical and quantum computers. I said before, you can see that this is the classical computer. Basically, you have this integrated circuit, the circuit model, logic gates realized through transistor that gives me 0 and 1, right? Either 0 or 1, switch on or off, right? Low charge and high charge. Now, on the other hand side, the quantum computer, you can see the similar kind of notion, right? I have the quantum circuit, and that circuit, the processor should be, placed in the quantum chamber. The bottom of this quantum computer, you can see that is the place that quantum the processor resides, right? That is the coldest place, minus 460 degree Fahrenheit. All right. So here I have given an example. You can use the electron as qubit, right? Because electron maintains two positions at the same time, or you can use the photon, right? Right. So there's many ways that you can realize qubit. And the bottom one is, and again, what I said, right? Look at this, as I said before, right? That is the power of quantum computing. The right-hand side, left-hand side, I have a 4-bit classical register, classical computer, right? Now with the 4-bit, I can represent 0 to 15 with 16 numbers, right? So with classical computer, I have to perform 16 operations, one at it, right? 1, 2, 3, 4, 5 to 16, right? The 16 operations, right? On the right-hand side, all 16 numbers can be done in one shot. All 16 numbers in a superposition, allowing truly parallel computation. Exponential growth with addition of each qubit. Look at this. I'm here. I need all 2 to the power 4, right? 2 to the power 2, which is 4. Now, if I to simulate or build qubit system with 20, 2 to the 20, how many states I can have? So Google, as I said, they use 2 to the power 53. So that's where this true power of quantum computer coming. The unique property of that makes quantum computing so special and offers such a unparalleled potential is that qubits, unlike classical bits, can also work with the overlap 0 and 1 states. And this is the example that I'm giving here. So that kind of, illustrating the power of quantum computer. All these things boil down to the superposition. And superposition is the game changer in future computing, quantum computing. All right, so this is kind of, again, electron right? So superposition of electron orbiting atoms, right? And I talked about all these things. Basically that, you know, the electron can exist simultaneously in two places. And that's the thing that we leverage in quantum computing. Okay. Another concept is entanglement. So we have one property of qubit, which is superposition, right? So the particle can be in two positions simultaneously. And another attribute or property of this qubit is entanglement, right? So this is very powerful. You know, this is powerful because, you know, if you can create a entangled, two qubits entangled, and one you can put in on Earth, the one you can put in the moon, right? So the qubit, changing any state in the Earth qubit will also affect the state of the qubit on the moon. So that is the kind of, you know, uniqueness that happens in quantum mechanics. And Einstein, Dr. Schrodinger knows better than me, right? And he also kind of baffled, he couldn't explain it. All he said that there is some unknown, you know, kind of parameter that happening here that we have no knowledge about. Why, you know, when the two qubits are entangled, I put one in Earth and other on the moon, you know, changing any status or state of the qubit on the Earth will affect the state of the qubit on the moon. So that is the property we'll be using in quantum communication. We'll be using that channel or spooky link to build the quantum network and or quantum internet in future. Okay, so in all these things you can see, you know, this is the qubit, and useful and powerful that it means that observing one qubit can reveal the state of other. And it's a kind of amazing, right? So now it's a non-locality here. Imagine that you have created a qubit. You can create qubit in your lab environment, and somehow you have created and you have put one in one place and one in other place, right? And this is the spooky link between two atoms. And this is amazing. Okay, so here we are saying if even we move one qubit to the moon, and the global state of the two qubits cannot be described solely in terms of individual state of each other. That means they're correlated. In particular, if we measure one of the qubits, this apparently instantaneously affects the other qubit. Okay, so this entanglement would be the key to the future communication, fully in a quantum internet that would let quantum computers of future communicate with one another and be immune to hacking. One of the things is that when this qubit is traveling from here to there, right? And it is unhackable, because if the hackers happen to somehow tap in this path of this qubit, right? It will be known. That means that the state of the entanglement will be destroyed. It will be known to the other side. If the hackers messed with this communication, it would spoil the entanglement, revealing their presence. So in quantum internet, and any node could be entangled with any other, so the message between them could not be decoded, you know, in the middle nodes. So that's kind of beauty that we will be leveraging in future communication, which is, we call it in the quantum internet. All right, so we can create the entanglement in many ways. It's one of the, for example, you can use this, create entangled photons, a special type of crystal to split one photon into an entangled pair of photons. A single incoming beam, in this case, for example, typically blue or ultraviolet, can thus conjure up to 2 beams, typically red. This process occurs particle by particle. Each blue photon splits into 2 red ones. So there are many ways that you can create entanglement. That is one of the requirements that you have to have in quantum communication. And here is, I'm going to summarize this. Well, not summarize, but basically you can see this quantum networking requires quantum channel with entanglement, and then it will require also classical channel as an example. So that is called teleportation. Basically, teleportation is that you can send a file from here to there without actually physically transmitting the file of bits. One will be sending the state of the bits, right? It's kind of difficult to understand, but that's how it is, all right? So this is my quantum internet, right? All I need the quantum channel. That means two sides are entangled. And then I need another classical channel to send the state of the qubit I want to send from A to B, all right? So here is this teleportation that the last talk Professor Moshiur Rahman explained, but it's basically, as I said, the qubit transmitted from one location to another related to an entanglement of quantum systems defined as a process by which qubit, the basic unit of quantum information, can be transmitted from one location to another without the qubit actually being transmitted. That means I want to send a file from location B, right? You can send this, just by transmitting the state. So this is an example quickly, right? So here's A and B, right? So I want to, send information from A to B. First thing has to happen, entanglement. That means A and B, I'll create an entangled pair of qubits. One will go to A, another will go to B. We call this entangled channel or quantum channel. Good, so A and B are set. Now I need another classical channel to send not the qubit, but state of the qubit that you want to send. So here the task that you see this arrow, right? So when these two routers or two locations are entangled, I want to send this information, this kind of qubit, right? You can see this wave function psi, right? I want to send this information from here to here. So basically what mathematically I can show, but we have no time. So mathematically we can join this entangled qubit that A has with this qubit that has information I want to send from A to B. I can use this, we call this tensor product, right? So I can mingle this two qubit and then only I send a state of this qubit and the A to B. As soon as B receives the state of this qubit from A, it will be able to reconstruct what A wanted to send to B, you see? So there is no need to send physically this file from A to B, always sending the state of this blended qubit A has, right? A has two qubits right now, right? So A will be sending this state of these two qubits to B, and from that information, B should be able to construct the file that A wanted to send to B. Now, one thing is that as soon as that file has been transmitted from A to B, that file should be destroyed, because in quantum, copying is not allowed, right? So there's another topic, right? So that's why you cannot teleport human being from A to B. It's not allowed, because that human being and a location A has to be destroyed in quantum world. All right. So that's an example how we will be leveraging this quantum computing for quantum internet in future. All right. All these thing concept, it is happening, in the real world from A to B, but in a very captive environment. Okay. So another thing I didn't mention, that you want to send like this qubit, where is that, from A to B, right? And you cannot, there is a couple of hundred kilometers that you can send. There's a distance limitation. Okay, you cannot go beyond that, kind of distance. So therefore, it is still a challenge to send this entangled qubit from A to B, right? It is happening in lab environment, but real world is difficult. However, you use fiber. We are doing, in different companies, you can send the entangled qubit from A to B using fiber, but you have to use a repeater in between to do that. Okay, so that kind of thinking we have in quantum computing. All right, so quantum internet, you can see this is the kind of architecture. You need three things, three primary tasks in this quantum computing. Entanglement, you have to have the entangle, right? These are the nodes, right? These are the routers, these are the locations. They have to be entangled first. And then you can send what we want to send using teleportation concept that I just described. Okay, you want to send, I call user data or your file from A to B, but before sending that, you have to have the entangled channel between A to B. Okay, So here is an example of, I mean, that that the Chinese has done. Basically, they have connected two locations, one in Australia, one in China. So they have used this satellite, right? As I said, there's a distance limitation sending qubit from A to B. However, they're sending this qubit to satellite. That's where they're doing some, repeater kind of functionality, and they're transmitting from there to this right-hand side. So that's they have done in 2016. All right. So let me see. And this is another, satellite as if Einstein's spooky action at distance. You can send qubit from here to here, and you can use this technique, or we call QKD, quantum key distribution, right? You send some file from here to here. You can use the quantum key distribution to make your information unhackable, right? And also teleportation, all right? So let's move on. And again, these quantum computers that we have talked about, the left-hand side, that's the computer that used by Google. Right-hand side is the IBM. But nonetheless, you can see what is the commonality. Basically, the hanging of the ceiling, right? And the bottom, that's where that qubit resides, right? That's where the chamber of qubit. Okay, that's where the temperature that we have to maintain. And that's why it's very difficult to have this kind of environment, in kind of normal situation or we call data center. So it will be challenging to have these quantum computers when it comes to real world, which is actually, maybe 10, 12 years down the road. Right, and so this is the Deva conditions to be free from all radiation, okay, and the temperature of almost absolute zero. And this is showing the left-hand side, what is inside this computer, right? You can see the outer closing here, the metal closing here, and the cavity of the stored qubit. That's the bottom of this right-hand side, right? So that's where that qubit resides. But you can see the coolant palm. That's the challenging part, right? That's the challenging part. It has to be, the certain temperature, right? So this is kind of challenge we have in building real quantum computer. Now, I already talked about all these things, right? So number one is basically that's the environment that we'll have to start with, okay? So the figure one shows that general structure of quantum computer system. The user basically, you can see user basically interacts with the classical computer if the problem requires optimization, right? The classical computer translates the user problem writing program into a standard for a quantum computer. That is the language that quantum computer will be, understanding. Okay. So the info is different from if another quantum algorithm is required. So the classical computer then creates control signals for qubits. But anyway, that's kind of another area that will take a lot of time to explain. Basically, the message here is that you cannot directly interact with the quantum computer. You have to go through some classical computer that will translate your program, and that can be, sent to the quantum computer, and you get the results back to your classical computer. All right. So here is kind of a structure architecture quantum computer. Now, some of the innovation landscape, right? See this. Right now we are 2020. You can see the computing market is 10.8 billion around in 2 years or so. And the key market segment of technology, superconducting, the trapped ion, these are the technique that we can use to create the quantum computing, right? So I mentioned some of them there. And then the top players in this game, right? Top players is, as I mentioned, IBM, Google, right? The Intel, Microsoft, D-Wave, Lockheed Martin. But tell you the truth, in the big players happen to be primarily IBM, Google, and D-Wave. Microsoft, they don't build any quantum computers. IBM does, and also D-Wave. In fact, the Google, the computer, quantum computer that Google has used, they bought from the D-Wave, a Canadian company. The computer NASA is using today, they bought from the D-Wave Canadian company. I think, as I said, they paid $16 million to use the computer, right? So the market segmentation, basically by end user, you can see, you know, the chemistry, the health sector, transportation, IT, telecommunications, right? Aerospace, okay? And by application, it can be the artificial intelligence, quantum computing, right? Encryption, that's the big thing here, right? We can use this quantum computing technique to have better encryption technique, right? So here again, some of the top applications, cryptography, then medicine materials, like the COVID-19, all the research going on, you know, when the quantum computer will be available, all those simulation, right? All the computation, you can see the power of quantum computing, right? In single shot, you can do things that would be impossible with the classical computer. And also the machine learning down the road, because machine learning, it deals with the data, right? The more crunching power you have, the better power you have, right? So the quantum computing will be playing big roles in this kind of applications areas. All right, now I just want to share this concept because I'm working in this area too, as Swell mentioned, the 6G. Right now we're working, just 5G is taking off, but we're only thinking 6G, right? Take an example here on right-hand side. Look at this. 5G, you have a file to transmit from, you know, so like the file size is 2 terabytes file, right? So in 5G, which is taking off, will take 5 hours. But 6G, when it comes, it will 18 seconds. Now, if I bring quantum computing on top of that, right? Think about it, the power. One of the idea, for example, the operation, right? The patient happens to be in somewhere in Moon, and the doctor happens to be in Atlanta, for example, Jahid or whoever, right? So you have to, you know, do this operation remotely. That means we're talking about, see this, you know, fraction of the millisecond. All these bits have to transmit in real time. All the movements that the doctor will be taking, right? All this, it has to be, you know, real time. So quantum computing will be playing big role there, that kind of thing. And as you know, I mean, as I know, NASA is doing a lot of research in using this artificial intelligence, machine learning, and quantum computing. Primarily this kind of thinking that they have in mind. Okay, so a milestone starting from the right. See, as I said, the quantum computer may not be available until, you know, maybe 10, 12 years, but nonetheless, the researchers are making progress, right? So right now, 2020s, we are doing some system level engineering, some prototype happening by IBM, by Google, right? By DOF, by NASA, but real computer will be coming in 2030 or beyond that. That's the time we say, you know, the commercial computers may be available, you know, for us to use. And this is top 5 market impact. As I said, you can see from the right to left, security. Now we talked about this, the blockchain, right? Blockchain will be obsolete when the quantum takes it over. Portfolio optimization, development complex quantum algorithm that, you know, that is impossible to do using classical computer. Fraud detection, banking, you know, all this, and the high frequency trading. So these are kind of, you know, top market impacts that quantum computing will bring. And here is kind of, you know, computing growth. You can see 2019, basically we are showing that, you know, what kind of improvement has been made in terms of computing power. Basically by that we mean how many qubits that can be realized to carry out computation, right? So right now you can see at the bottom, this is, you know, the Google is last year did 53, but they have this lab environment that can be, you know, utilizing 72 or more than that. And this Rigetti, the company, you know, they are doing about 200 qubits. It's more than this old slide, but, you know, 200, more than 128, right? So you can see the technology improvement happening, right? And so it's another, the annual spending. This is, I think I have this snapshot a year ago, 2 years ago. but nonetheless is giving some, some perspective of the annual spending. You can see that the whole Europe is in terms of the pound sterling, right? And you can see that America is spending this and the whole world. So the things are working and people are involved, and governments and private sectors are investing, in this thing. In fact, if you, those universities, I know they're getting, good chunk of funding, because this is a new area. A lot of companies are trying to, test and do this kind of experiment and giving a lot of money. And universities are getting, a lot of opportunities to carry out this kind of experiment. So there is, the big amount of money being spent on this experiment, on this expedition or technology evolution. So here is the slide I put primarily for the students, because, students don't understand. They understand what is for me, right? Programming, quantum computing language program, right? So you can see on the top, a student will be sitting, working on the classical computer, will build a program, right? And the program will be, compiled and will be downloaded to the quantum computer sitting in the somewhere, right? And then when the quantum computer is done with this computation, it will send the result back, and the result will be a kind of presented in terms of classical output, right? So that's kind of view we have. And main idea of the quantum computing, you see, you have to manipulate, in our classical computer, what do you do, right? We manipulate the bit 0 and 1 using transistor, right? So if I have this, there's the electron, the circuit, right? The transistor on and off. We manipulate transistor, right, using gates. In quantum computing, in the right-hand side, we have to manipulate the qubit sitting right there, right? I want to manipulate qubit because you have seen 0 and 1. I want to manipulate that 0 and 1 so that I can carry out more calculations. And you don't have to understand this. This is the one of the circuit. This H, Hadamard gate, used to create superposition. This kind of thing we used in quantum computing. This is the circuit we'll be using, and that circuit will be translated to command the quantum computer to do this, right? So that's kind of thing we do in quantum computing environment, right? So, right, so this quantum computer. And the classical logic gates versus quantum logic gates, the left-hand side, again, the manipulating the bit using transistor, right-hand side manipulating the qubit using this kind of gate we call the quantum gate, right? Hadamard gate. Again, I'm manipulating 0 and 1. And Hadamard gate, as I said, is used to create superposition in a computing environment. In the lab environment, I think Professor Moshiur Rahman knows, they use this, they call beam splitter, right? You can create beam split, you can use beam splitter to create superposition, right? And you can see the, what kind of thing we want to show to students, right? So the superposition is created by the beam splitter. And, there's an experiment we call Max Gender experiment. That experiment shows that a particular photon or, a single photon can be, traveling through the quantum chamber, right? So a single qubit can take 2 paths. One photon can take 2 paths simultaneously inside the superposition. And I tell my students that superposition, you cannot see it. Only God can see it. Right? As soon as you measure it, it's gone. So again, the quantum computing is already a number of programming languages exist, but there is no actual computer to try it. The purpose of quantum programming language is to provide a tool for researchers, but nonetheless, the students can access to this quantum computer sitting on the cloud, and QCL is one of the example of this language. All right. So just give you some, this is the quantum programming in Python. Here we're doing that. We are creating the program, which is creating a qubit. Then I'm using this Hadamard gate H to manipulate the qubit. And all I do this, I create this classical computer, I compile it and send it to the quantum computer and then get the results back. All I'm doing to manipulate the qubit, right? The qubit is a kind of particle, and the gate is this kind of process, right? I use the process to manipulate the qubit to get desired results. Okay, so again, this is a programming quantum computer example here. On the right-hand side is a visual representation of qubit. Again, this uses 0 and 1, but we are interested between 0 and 1, right? All the positions that is vector, the qubit taking, right? That's the position we're interested in. That's the magic, superposition. So some engineering challenges here, like, you know, the long living qubits, because when we create a superposition, it doesn't, you know, live long. It's difficult to sustain that environment, right? And the separation of control, decoherence, scalable implementation. By that we mean, you know, you have seen this, right? If I want to use this quantum computing environment in quantum communication, it is not, you know, easily scalable, because you have to maintain that kind of environment, and it's quite expensive, right? I mean, logistically and financially. And this cost associated with this cooling, right? You see this 460 Fahrenheit, that is 100 times colder than interstellar space. So new quantum models, again, the challenges. And right now we have only two algorithms, which is, you know, this factorizing and searching for database, right? But we need more algorithm to make this quantum computing, you know, more meaningful down the road. And of course, getting funding. So that's kind of engineering perspective or challenging that we have. So to summarize this thing, classical computer, it can have 0 and 1 to represent the information. The quantum computer, it can have the qubit, 0 and 1, which is superposition, right? And so this is the superposition. You can have 0 and 1 simultaneously. That's the magic. And then entanglement. So it's kind of entangled. You create two qubit entangled. You send one here, other there, and they're entangled. Therefore, whatever you do, you know, at the local one, observed here, affected over there, right? And then right-hand side, this is quantum networking that leverages quantum computing. Teleportation requires the quantum entanglement, we call quantum channel. And also we need the classical channel. And that's how our internet, quantum internet will look like, right? You need this A and B connected. You need the quantum channel, which is entangled, right? It's a link between A and B. And then I need a classical channel to make this work. And finally, so there are a lot of people asking, so what, right? What, you know, what the quantum computer be like, right? I mean, as you see that, you know, I have gone through this kind of environment. You need this environment to maintain this other quantum computing, right? So it is right now, you know, this is very difficult to build quantum computing environment, right? And in reality, the qubits would have to be stored by atoms, right? Or ions, atoms with too many or too few electrons, right? Or even smaller things such as electrons and photons, right? So the quantum computer would be almost like a tabletop version of the kind of practical physics experiments, for example, the Fermi lab is using. Now you won't be, you know, racing particles, right? Particles around giant loops, smashing them together, but you would need mechanism, right? You need mechanism environment for containing these particles, atoms, ions, right? Subatomic
Sorry
particles.
for interruption. We have a lot of questions also. I just wanted to let you know.
Okay, good. So I'm almost done, 2 minutes. Good. So then what can quantum computer do that ordinary computers cannot do? Well, I have given some example, right? I mean, that kind of factoring, right? Prime number. So there's a lot of problems that will be difficult for a classical computer to solve, right? Simulating the universe, right? The molecules that you want to simulate, to experiment with. So those kind of things could not be done using the classical computer. So then why is so hard? Well, so it is hard because you have to have this, you know, special environment, right? And so all these things, you know, making very difficult to quantum computer, you know, to be commercially available. Now, how far how far off are quantum computers? Well, as I said, it is too early to be able to predict the time horizon for a particular quantum computer, but consensus here is that it may be, about 10, 12 years down the road. Okay, so that's all I have. And we can go to Q&A, right?
So
Sorry,
I'll take it over.
Go ahead.
I'll take it over from here. Thank you, Dr. Moshiur Rahman. I'm pretty sure, at least me, I have a lot of questions. So I have to spend maybe hours and hours just to figure even simple things out. But I know we have a lot of professionals, engineers, scientists. They probably got some of them or most of them. But at the same time, I will let you drink some water or something like that. I will touch few base things in the meantime. Number one, our first session we did on cybersecurity, which is available to in YouTube under Keep Talk. There are a few sessions, which was done by Rakib Hassan. He's a student from Buet, and he's also working in cybersecurity world. Second, we have Professor Shafiqur Rahman. He had a session which is also available in YouTube. You can watch if you would like to, which is on quantum teleportation and is our universe a massive computer simulation. Also, this is the session we had on quantum computer and networking. Thank you to Dr. Moshiur Rahman on this. Coming up in 2 weeks, we are going to have a speaker, guest speaker on 5G. And then we are also planning to have some other speakers on Industrial Revolution 4.0 and some medical advancement and technology, how it's changing the world today. That said, also, I do appreciate your joining us. First of all, we are going to address some of the questions. So what I'll do is I will read out to our guest speaker some of these questions. And once this queue is done, we will unmute everyone and you are welcome to ask more questions and you can hang out with them. At some point, as you know, this session is being recorded. So at some point we are going to stop the recording and then you can still be in the session, but it will not be recorded, but you can talk on one-on-one to our guest speaker for tonight. So given that, one thing I mentioned, which Dr. Moshiur Rahman told me to mention, and I think he touched. So we just want to be clear is that quantum, when we speak about it, it is actually an intersection in between physics and computer science. So it's going to complement many things. And that's why I think many scientists, they're very, very excited, as well as we have some computer science people here. They're also very excited to see the computing power. So I'll go to the Q&A. This question come from me actually. First one, I'll take the leverage on this, which is what I heard is the temperature has to be 0 or sub-zero for the quantum computing or quantum fusion, whatever you say, I'm not sure exactly. But so why has to be at that level and how do we compute being at that level? Is it feasible for normal general people or general computing? Second is how far are we from achieving quantum supremacy? I'm giving you some time so you can drink your water and breathe a little bit. So I can repeat all those again if needed. The other one was 0 to 1 example, how it is different from fuzzy logic. So I'll stop at these 3. We have at least 5 more. Are you ready to answer some of the questions now? Or
yes, yes, no, okay. So the first one is that, why the temperature has to be so low, right? So the simple answer is that, when these qubits are, isolated, well isolated, right? So these qubits heat up quickly. So keeping them cool is important. So that's how, we have to have that level of temperature in this environment. Okay. So just to, maintain this, because when this kind of chamber, the qubits heat up quickly because of this, the loss of, heat from that. And as I said, when our iPhone, right, it becomes hot because there's the loss of heat, and that information, the loss of information, that makes this, call this heat, right? So that is the reason that we have to maintain this temperature that low, which is 15 millikelvin and equivalent to 273 Celsius, which is 465 minus 460 Fahrenheit. Now, the second question is that quantum supremacy, right?
Yes.
So, Google has claimed that, right? So what that means, the supremacy means that, where the quantum computer supersedes classical computer, right? That's the meaning of it, right? And Google has shown that, right, in their 53 qubit experiment, that the 200-second operation would have taken 10,000 years for classical computer. So, how you define supremacy doesn't matter, but they have claimed that the amount of time that 200 millisecond operation they have carried out in this captive environment for a specific problem that would have taken like 10,000 years, right? So that is kind of relative terms quantum supremacy, right? But actually, when we talk about the reality, how this all will be playing out, that is, to be seen. But right now, Google has demonstrated that that particular operation that they have, shared, but IBM has said that, they could have done it with using classical computer in 2.5 days. All right. So what is the third question? Is that?
Sure. Also, Dr. Moshiur Rahman, if you don't mind, stop sharing so we can all see each other. That will really help a lot. If you put stop sharing, then we can see all of us.
Oh, sorry. Okay.
Yeah, thank you very much. So the next question comes is 0-1 example, how it is different from fuzzy logic.
Well, fuzzy logic doesn't use, like, the quantum environment, right? So basically, 0-1, it is, you can say any number, right? But we happen to use 0-1 because that's the expression we're using in a classical computer, right? So this is basically the position of the electron or photon or particle, okay? And so we are interested in that, the position of the particle between 0 and 1, physical position, right? So simultaneously happening, and the calculation can be carried out using this. But fuzzy logic, I don't think they use in this kind of physical means, right? Which is the particles, right? The electron, photon, or neutron, right? So that's the difference. It is different. It is fundamentally different, right?
The next question came in, and I think it got answered, but I will just make sure this was answered. How do you program a quantum computer? What kind of special language do you use? I think Professor Shafiqur Rahman said on this one is QCL, and I think you also said the same thing.
Yes. In fact, and there are so many programming languages. IBM has IBM Q, right? They call it Qiskit. In fact, I use that program, in my class. So IBM has this Qiskit, and Rigetti has a similar kind of package. So basically, what they have done, the quantum computing is a package of classical cores, right? So you cannot directly talk to quantum computer. You have to write your algorithm in classical computer, and primarily we are using this Python language, right? And then that language, this algorithm is being translated by a compiler that this company has built, IBM, for example, right? I built a program, and then I submit to this IBM environment, and then the IBM takes it and sends it to their quantum computer, and then quantum computer is done, sends the result back to this classical computer, and then you can see that, right? So there is no direct connection between the programmer and the quantum computer. You have to go through this compiler, which is direct connection with your classical computer.
Okay, thank you. The next question came from Tawhid. It says, what value would quantum bring to general population?
Well, you see, I didn't mention it. See, I mean, quantum computer will not replace classical computer, as we see, right? So that is, I mean, it will be, in different paradigm, but quantum, I think Professor Shafiqur also mentioned in his talk, also I have, from my research, right? So quantum computer will not replace the classical computer. It will be there. For example, we don't envision iPhone to be iPhone Q, right? Because first of all, you cannot have this kind of environment, this qubit chamber in iPhone, right? Maybe, I don't know, 100 years or 50 years, we don't know. But as of now, general public, but, think about it, right? You are using your computer and you're connecting from here to the moon or somewhere else, right? So your quantum computer bringing this parallelism, right? The parallel computation. It will shorten your duration, transmission time, right? So general public, they won't be able to use it as we are using this classical computer, iPhone, right? It's classical computer, but we will be the indirect client of this quantum computing environment in the future.
Thank you. The next question comes from Rodion, who is joining from Austin, Texas. He also speaks Russian or some language, I think Russian language. So anyhow, his question was, does a quantum computer allow to implement a non-deterministic Turing machine?
Well, as I said, the quantum is probabilistic, right? Because when you say 0 and 1, right, it's a probability, right? So depending on the vector position, right, if it is, I have said that alpha and beta, right? So as soon as you measure it, right, it gives you deterministic answer, right? So it cannot be used as is, right? I mean, it cannot be used because you have to have this physical environment to have this thing done. Therefore, it is probabilistic, and the environment is also probabilistic because 0 and 1 position, right? It is not definite. When this electron is racing in the chamber, right? They may be 1 and 0, but we don't know until we measure it, right? So you have, number one, you have to have the environment first, and then we have to have the result we call in the measurement, right? So sure. Maybe Professor Shafiqur can also add to this from his physics point of view, but that's I see in computing, kind of, environment.
So there are a few more questions, one from Kamrul Bhai, from Bihas, and some other people. I haven't seen, surprisingly enough, any questions today from Melbourne or Sydney. Usually I'm very used to 5-6 questions, but I am guessing they're going to ask in person. We have some talented people also joining from Australia.
Yeah, we send some materials to Nazmul, right? We send
materials for any further questions, if I may say, you can unmute yourself. Some of the other questions you have, unmute yourself and just show your hand so Dr. Moshiur Rahman can address you and take your questions one by one. I think that'll be more interactive than me asking the questions. So please go ahead, just show your hand so he can address you. I think Mr. Bivas has a question. Dr. Moshiur Rahman, please, are you ready for him?
Yes.
I have a couple of questions, 2, 3. I'll like, my first question is, like, is hardware download possible by this like quantum entanglement?
Hardware download quantum entanglement?
Yes. Like, as you were telling that I'm not a computer engineering student. I'm a mechanical engineer, but I have always interest for sciences and physics. So, like, my thing is, if I'm understanding rightly, like, quantum entanglement is something there is no, it is independent of the distance. Like if something is 1 light year apart, like one thing is here, another thing is 1 light year, and we know that for any information, it cannot travel more than the speed of light. But regarding quantum entanglement, if the 2 subject is 2 electron or 2 photon is 2 different places, like one is here and another is 1 light year, does time needed to so like you change something here and that is changed in the other place, like 1 light year apart. So does time needed or not? So like this, if you change here, is it possible to download something like hardware download?
I mean, I don't know what you mean hardware download, right? Two things. Please. Entanglement, basically, you can create entanglement of, physically in a locally, right? So the way it works, right? I mean, in communication, so you can create entanglement using any physical device, but that means you blending 2 qubits, right?
Yes.
So they're entangled. One is up, one is down, right? So now you separate this and send one here, on there. So that is, entanglement, a kind of a link or connectivity, right? Spooky link at a distance, right? Now, the quantum mechanics, right? That EPR, so it tells us that, any state change, any one of them will reflect the other one. So that is the nature of this, of this quantum mechanics, right? And that is the spooky action at distance. And Einstein said that there are some properties that that we don't have knowledge about. It happens, right?
Does the spooky things exist in natural phenomena like this? Like, is it possible? So, like, we want to develop, like, we want to do it for a physical distance, like you told that by a satellite. Chinese people, they have done for one Earth from Australia to other places. You have developed it. You have done it by like any physical things, like a quartz or something. You have passed something through some crystal, or you change the blue light to red lights. So, is it in naturally exist this quantum entanglement?
Let me track that, because it's more of a physics question. Yes, in nature it does exist. For example, if you consider a cosmic particle that we call a pion, it disintegrates into 2 particles, an electron and a positron. So what happens is that each of those 2 particles is a combination of an electron and a positron. So there are systems in nature where there is automatic entanglement between particles.
Okay, I got it. Yeah.
Now let me go back to the question that you asked before, right? I'm trying to see if I understood your question correctly. What are you trying to ask? Whether one could download information very fast? Yes. Is that what you were asking?
No.
I'll take this. I'll take this. I'll answer your question. Hardware download means there was a thesis, there's a proof from University of Jerusalem that sorting of 10 million and sorting of 10 billion will take exactly the same time. We know that when you have got number of units increases, sorting time, a lot more time, right? But it says a constancy. It says that sorting of 10 million and sorting of 10 billion will take exactly the same time if you have got infinite computing power. So hardware download means adaptive hardware. Some hardware are big in cores. Some hardwares are big in number of cores. So small core, but a large number, right? And every core can do only a few things. But you can have computer where one single core will do very, very large thing. With a hardware downloadability, it means that computer CPU can adapt itself to change based on the requirements. Now, that is a totally different concern from the quantum computing. But of course, you can configure a quantum computing with this added concept so that it can change its shape accordingly.
Right.
My another question was my last question. That question was my understanding was like you told many times that we have to maintain 15 millikelvin temperature. That is very, very, very close to absolute zero. It's 0.15 degree Kelvin. So is it for to make the state of the, like you have to contain that quantum like qubits in a place, like it could not be a physical space. It may be so regarding that, is this low temperature to make the particles or the space very, so nothing will move, like no movement will be there, so everything will be freeze, like
exactly. I mean, exactly. So that is the only right. So we want to make sure that the atoms, right, are not moving. Right. So that is the only way, giving is to slow down the movement of atoms. So a qubit can hold a value, right? Yeah. So that is the requirement, that in order to have that, so that qubit can store or hold a value.
Okay, thank you.
Any questions?
So the way people explain entanglement, the actual situation is a little more complicated. So let me try to explain this. Let's say you have two entangled particles, right? You have one at your location and you send the other, let's say, very far away. And you want to teleport a particle from your location to the other location. So what you do is you take the particle you want to transport and you entangle that with the particle you have, right, with one of the entangled particles that you have, right? Now, when you entangle two particles, there are 4 possible results that are highly probable. So you really don't know which one of these 4 took place unless you check. So what happens is that, yes, at the other place, the particle has assumed that property, right? But it's not yet fully in that position, meaning basically it can be one of 4 possibilities over there. So you have to send the key as to which of the 4 possibilities has taken place where you did it. So that cannot travel faster than light, right?
Yes.
So ultimately, you are bound by special theory of relativity. So that key as to which one of the 4 possibilities took place, that has to be sent by a normal channel. And then the person at the other place has to use that key to extract the information from the other entangled particle. So as a whole, operationally, you really cannot extract the information faster than light.
Yeah, exactly. Right. So that is teleportation, right? What just Professor Rahman explained, right?
Yeah.
Good.
So there are a few more questions, for example, and then Kamrul Bhai has one more question, I know, but he's muted, so I'll take the leverage to ask my question, which is somebody was asking, what are the top research universities in QC, quantum computing? And the other part is there a good introductory textbook on quantum computing? In our department, we understand it's a hot area, but no one has any experience.
Sure, let me share this. In fact, can I share this? I have this, I can use, I mean, I have 2 books I use, right? So I have a syllabus too that I have prepared for Princeton University. Can you give me sharing? I can share and then maybe I can send it to. So this is the, all right, share. Okay, so let me see. You see this, right?
Mm-hmm.
So you see this, right?
Yes, we can see.
So this is the, I mean, again, this is the syllabus that I have prepared for my fall lecture. I mean, I did this for Princeton as well. It's our graduate course, right? You can see this, the 2 books. The first one is very simple to understand. It gives a lot of linear algebra description, fundamentals of quantum gates, right? Algorithm. It's a very good book for the beginners, right? And the other one is little bit, I mean.
Different areas, computer science, in AI, and I'm in program analysis, where we build the state machine representations of the software to analyze it statically, like find out if there's a possibility of deadlocks and so on and so forth. Any kind of speed up like this would be a great contribution, but no one understands so far the physical from computer science.
Yeah,
like,
I mean, in
we
fact,
don't understand the physical underpinnings. It's like you have to be a physicist to do this. You have to understand these wave functions, Hamiltonians, at a practical level.
Yes, yes. And that's why, I mean, from my work also, I am collaborating with IBM. They have the lab in New York, right? And also we have, I should not, anyway, we have this, our own company. We are working with Caltech and also Farming Lab. And, there is something that I am also doing through my students at NASA, right? So there are a lot of collaboration happening from academic side. And so those are in public domain. But anyone wants to know a book, I would recommend this very simple book, right? Written by Indian guy, Parag Lala. It's very easy to read, easy to understand. And it's very simple way that he has explained this quantum math foundation, as well as the quantum gates, and then the classical gates, and then taking to teleportation next step. So I would recommend that book is good. And then this second one. Yeah,
the other question was about the top research universities in QC.
Yeah, so the top university, right now, this says one is Caltech, all right, and Princeton is not that, they're offering the undergrad course, but not, so they're doing something, but this Caltech and one university I forgot in Australia, very active, and one university in Netherlands, and University of Maryland are doing a lot of research, I know, and they're getting tons of billion funds from government too. So University of Maryland, one of the places that I know, doing a lot of research, and the Caltech, and one university in Netherlands and one in Australia. MIT is doing, yes, MIT is one of them too, right, in MIT. So these are the 4 or 5 top university, university involved in quantum research, right?
Outside this country, University of Innsbruck, they were one of the first people to do some substantial work.
Yeah.
And here, also University of Colorado, I think a few years ago, they got a $200 million grant from NSF to develop a quantum computer of, I don't remember how many bytes.
Right.
How many qubits, right? But the fundamental research, that's really some of the places that Moshiur mentioned, and then overseas University of Innsbruck is one. There is a university in Germany, I forget which one.
Yeah, I know, yeah, there's one, yeah. So this kind of experiment, let me tell you that, for example, Farming Lab in Chicago, they are collaborating with the Caltech. I know that, So IBM is doing similar thing with some universities in New York, right? And so it is just evolving, and companies are, giving money, a lot of universities like that. Government also doing. In fact, China, China is leading in patent of quantum computing and 6G. It's more patents than the United States. So you see all this, I guess, evolution and development that they have done, the satellite connectivity, using the 2 locations in Vienna, and China, right? So they are really heavily involved, and they're spending. Chinese government is spending a lot of money. In fact, China and USA in, competition is 6G too, which is interesting thing that 6G will be happening 2030 or something. Same thing, projection of this quantum computing around that time frame, 2030. So there's overlap in kind of this 2 technology that might be, So again,
that's probably hard too, because what I was watching is that in 5G, China is got the most patent, number 1, and number 2, they already start investing into billions and billions into 6G. So
Right.
and
Yes.
that's why we are falling behind day by day in this 5G and 6G.
Is not sufficient. So what you do is you use liquid helium to go to 4 degrees Kelvin, and then you use a technique called nuclear demagnetization.
Yeah.
With that, you can go in millikelvin.
I see.
Yes.
Yeah.
And my go ahead.
I worked for Beximco Pharmaceuticals while I was living in Bangladesh. They have their NMR machine. So I use this personally. In the outer shell, they use the liquid nitrogen to come down to -196.
Yeah.
Then from -196 to -269, like 4 degree Kelvin, you can go by liquid helium, then to protect liquid helium loss. And then you can go by magnetic cooling.
Yeah, that magnetic cooling is the nuclear demagnetization.
Yeah, right, exactly.
Yeah.
Okay.
Yes. I mean, that's the beauty of it, I mean, it's a nature, right? It's a nature that's doing it for me. And, it's like, using 2 hands simultaneously, right? so the two positions and then multiple and the computation happening. So that is the key and the beauty of this, this superposition of these quantum particles, it's just, it's amazing, right? I mean,
Kamrul, an interesting analogy would be the following. You can think of let's say, a mango tree, and there are mangoes, and you want to reach each one and do something. Maybe you want to spray them or pick them. So you can go to each one individually, or if you have some kind of a method, you can shake the tree, and then every part is affected, right? So in quantum mechanics, that's what happens. If you touch one part, everything is affected, not just that part.
Yeah.
Okay.
Yes. Doing one, you are, in fact, manipulating everything.
Because they're interconnected.
Yes.
They are in superposed state.
Superposed. 2 things, interconnect, yes. Superposed. They're superposed, right? You're doing one thing, you're affecting everyone in that group. So.
Got it.
So anybody has any other questions?
I have a last question. I'm
Please
asking
go
too
ahead.
many questions. I'm sorry, but
Please.
You know that always I have many questions in my mind. I cannot finish the question, but I have to.
So you should attend my class maybe, right?
Time,
So
as long as our guest speaker has time for you, please go ahead.
Just
go ahead.
One question. You told that the Google has developed for using 53 qubits. So that is almost like, if I'm understanding the right thing, like you told that if there is 2 qubits, then you can take 2 to the power 2, like 4. So by one operation, you can discover the position of 4 states. Like 2 to the power 53 is 9 into 10 to the power 15. That is huge number. So is that correct that if Google is using 53 qubits, so almost 10 to the power 16 operations can be done in a single operation by quantum computer. Is that correct?
You see what is happening. I let Shoik Bhai to do it. So what is happening, so you see how many bits you're talking about, 53. So how many positions, how many configuration we call it, right? So 2 to the 53, right?
Yes, correct.
So as Shoik Bhai said, right? One operation with 1 bit, right? It is affecting all of them simultaneously, right? The same time, single shot, right? So you see how many, there's a physical time also involved here, right? How many qubits you are doing in one single shot, right? So yeah, that is the thing that happening in the quantum.
But now my question is coming. So why people are going for more and making it is like 53 qubit is huge, and why people are going to 200 because managing so many qubits is very difficult physically to hold the things. Why people are asking for that? Why people are looking?
Let me answer this, because this is connected to physics and engineering issue. When Google claims that it's using 53 qubits, these are not fully independent qubits. So what they showed was that a particular problem that's specially suited to quantum